Good morning. Today's lab, we are going to do some measurements of the Earth's magnetic field right here in this room. So as you know, the Earth's magnetic field is going to vary from location to location. So we have to be very specific about where we're making the measurements, and we're making the measurements here. And magnetic fields have direction, they're vectors. And so we need to report components of the magnetic field. So we'll write that as Bx, By, and Bz in this room. Now, for the coordinate system of the room, let's do this. Let's say that this way is x. So if we move along the table edges, if we align with the table edges, that's the x direction. Y is towards the front of the room. So if I'm looking in the y direction, this is y, this is x. What do you think z is going to be? And if we stick with right-handed coordinate systems, which is our convention from math and physics, if x is here and y is here, then z needs to be up. So we're going to say the positive x direction is here, negative x is over here. Positive y towards the front of the room, negative y towards the back. Positive z is up, away from the surface of the Earth. Negative z is down. So that's the coordinate system of the room. Now, something to be aware of is the room is not aligned with north, south, east, west. So it turns out that this direction is not really north. North is actually shifted. There's a rotation of about 25 degrees, but we're not going to worry about that right now. Let's take a look and see what we're going to be doing in the lab, and then we'll deal with this, rotation of our coordinate system later once we get to that. So first of all, here is Earth, and as you know, Earth generates a magnetic field, so there are currents of charged particles, likely some combination of electrons and nuclei, in the core of the Earth that are not moving at the same direction. And so their magnetic fields don't cancel out. There are these self-sustaining currents of charges within the Earth. And so we've got this magnetic field. Now, Earth's magnetic field is not, it has a geometry to it that we refer to as a dipole shape. And a dipole shape says, hey, it's almost the same as if we had just a very simple bar magnet. If we have bar magnet, we are going to be able to show what the field directions look like. So here is the north end, here is the south magnetic pole. And so the field is directed away from the north end towards the south. Now what that does give us is that if I've got a compass, the compass aligns with the magnetic field, and that points to the north, geographic north of the planet. But that actually corresponds to the south magnetic pole. Not a concern for us. The other issue here is that there's a rotational axis of the planet, and that the magnetic field doesn't line up. The magnetic field is shifted like 10 or 15 degrees compared with the rotational axis. So magnetic fields of planets don't necessarily line up with their rotation. Whatever's generating these currents, whatever's maintaining the currents, those currents don't necessarily have to line up with the rotation of the planet. All right, so the reason this picture is here, we're trying to make a prediction of, in this very room, what should the magnetic field components be like? Well, if we are here somewhere, we're at somewhere, 38 degrees north latitude, something like that, 37, 38 degrees north latitude, we should find that the magnetic field orientation at this latitude has a very large downwards component. In fact, our largest component right here is the downward component of the magnetic field. Now, in addition to that, in addition to the downward component, the large downward component, we have a northward component, which you would expect, right? Magnetic fields are directional. They point more or less northward. And so we're going to have a component towards the north. Now, as I was saying, north is not actually the x direction in our room. It's shifted 25 degrees. And so that says, I'm guessing we're going to have a component in the x direction, and I'm guessing we'll have a component in the y direction from that. So I'll get both x and y. Now, it turns out that not only do we have a downwards component and a north component to the magnetic field, we also have an east component. Remember, we said that the magnetic field doesn't line up with the rotation of the Earth. So we actually have, let's see, if this is north, this is east over here, we actually have a little contribution from the east also. And so what that does is it tips our magnetic field. So the magnetic field is not directed northwards quite. There's a little bit of an east component to that. Okay, so it could be that that almost cancels out. Within the room coordinates, that almost cancels out the y component. Okay, so what we're guessing is this. We're guessing that there's going to be a large downward component to the magnetic field. And when we say large, Earth's magnetic field, has a value of 40 or 50 microtesla. So this is just relative in size. So it's a pretty modest magnetic field. But we're going to have the largest component downwards in the negative z direction. And then we're going to have a pretty good sized component in the x, we're guessing. And then it's not sure in the y. We could have a small component in the positive y, or even a small component in the negative y, depending on how shifted Earth's magnetic field is. So in any case, how are we going to make this measurement? And what we're going to do is we're going to use an electron beam. Now, this is our electron beam. And what some of you may recognize is, it's an oscilloscope, right? It's used to measure voltages and currents and set up different circuits and analyze them. But oscilloscopes are basically an electron beam. What they do is they have a vacuum tube inside, where at one end of that tube, there are high voltages that are generated inside here. It turns out that our oscilloscope uses 1,000 volts to accelerate the electrons. And so there's a 1,000-volt region concentrated at one end, and then the electrons pick up speed, and then the rest of the way they mostly just drift. So what happens then is that, let me turn on the oscilloscope and let's see what it looks like with the electrons hitting the screen. Now, usually with an oscilloscope, you probably have seen this as having a horizontal line, or maybe some kind of a sine function going on with that. But what we're going to be using it for is just an electron beam. So I've turned off the horizontal gain. I just scaled that all the way down. So what we're thinking in terms of is, hey, it's an electron beam. And it's pointing towards the screen, and those electrons are hitting a phosphor coating on the screen. And the phosphorus is what generates the photons of light. When an electron hits, the phosphorus generates a photon of light, and we can see those photons. We can't see the electrons. We can see the photons, particles of light that are generated. Now, it's really bright right now. I put it bright to make sure, I hope you guys can see that. What I'm going to do is I'm going to turn down the intensity. Now, I think this is kind of funny that you've got these controls on the back of the oscilloscope, because shouldn't you have the controls on the front where you can watch and see what effect they're having? So let me see, I think this is intensity. Yeah. So I've turned it down. Now, you guys probably can't see it now, but I've turned it down and I've focused it. There's also a focus on the back. So I'm turning it down and I'm focusing it. Here it is. Because what we want for our measurements is one tiny point that we can follow. And here's why. So what's going to happen with these electrons is, okay, I got this beam of electrons. It's being generated inside the vacuum tube. And the electrons head out, and they're headed towards the other end of the tube, towards the screen. So here are these electrons, and they're going really, really fast. And they hit the screen, which is right here. What happens if there's a magnetic field along the way? Well, if there's a magnetic field, the electrons are going to get deflected because they're going to experience a force. Let's imagine that I have a beam of electrons generated using 1,000 volts. How fast are they traveling? Well, if the voltage is 1,000 volts, I can say that the kinetic energy then is the charge times the voltage, and that gives me 1.60 10 to the minus 19 joules. And then I can take the kinetic energy and use the kinetic energy and the mass of the electrons to solve for a velocity. So the velocity I came up with was 1.87 10 to the 7th meters per second, and that's pretty fast. That's like 3 or 4 or 5% of the speed of light, right? So that's those electrons are really moving at a high speed. So as the electrons come through, if there's a magnetic field present, so for the magnetic field, I drew a bunch of X's. That's our standard notation for a magnetic field directed into the board. So let's see what the vectors look like. I got velocity in the forward direction. I've got a magnetic field into the board. Now the electrons are negative, so I'm going to actually use a left-hand rule here and put my thumb in the direction of the velocity. I'm going to put my fingers in the direction of the magnetic field. And what that tells me is the force is the direction my palm is facing. So I think the diagram here works, given the orientations we've set out. The force on the electrons, as they head off towards the screen, is going to be in this direction. Now, they're clearly reaching the screen, so it's not like they're being deflected so much that they never get there. But there is going to be what I'm going to call a deflection. So this is where they would have hit if the magnetic field were not here, but this is where they're actually hitting. So now there's a set of equations we can use to kind of step through this. To a pretty good approximation, we can just use constant acceleration. We can say the deflection, the displacement that takes place, the sideways displacement. Remember, this is perpendicular to the velocity. The perpendicular displacement is given by 1/2 AT squared. The acceleration is the force divided by the mass. Now that's the mass of an electron, and that's going to be equal to force, will be the charge times V cross B. You go, oh no, it's a cross product. Cross products are impossible to figure out, right? Okay, so I put together some notes. So take a look at what's on the board, take a look at what's on the notes that I've posted to Canvas, and go through those and see how this is going to work. But yeah, we do have, it's a three-dimensional lab. So I guess they're all three-dimensional. This is a three-dimensional lab where you have to actually think in terms of all 3 dimensions. And so, well, let's see what this leads to. I need to know time. I've solved for the acceleration here. I've got velocity. We talked about that up here. I know the charge of the electron. I know the mass of the electron. But I need to know how much time it's going to drift through the field. And that's determined by the length divided by the velocity. Now the length is about 25 centimeters. So if I open this up, it turns out this tube is not the same one that's in here. In fact, this tube is longer than the oscilloscope. But we have opened these up. And when we open up, we measure those to be about 25 centimeters. So the drift distance. So that's definitely just a bit of an approximation for sure. But L over V, I can substitute that in. Here's what I got, is that the deflection is given by V cross B. Now there's a couple factors of V here. 2 times the mass, the charge of the electron is minus E. And then there's a length squared that shows up. So that's kind of the formula. Now that's got too many things going on because it's three-dimensional. So what we can do is this. The idea of the lab is, first of all, to do a set of measurements that we're going to call x velocity. So let's say that I've got, oh, it lines up with the board. So here is x velocity. For x velocity, I'm going to take the oscilloscope and line it up like this. And so I've got the electrons going in the x direction. And then I'm going to look at the screen. And what's going to happen at the screen is this. As we rotate, I'm going to rotate the oscilloscope. What's happening is this. Let's go back and look at this picture one more time. Let's say that in order to measure this, what I would like to do, ideally, what I would like to do is turn off Earth's magnetic field. Now when I turn off Earth's magnetic field, what happens to the trajectory of those electrons? Well, if I turn off the Earth's magnetic field, it's going to land right there at the center of the screen because that's how we've adjusted it, sort of. But when I turn the magnetic field back on, then it's going to get deflected. I can measure that deflection, and then I'm done. Lab is done. The problem with that approach is we can't turn the magnetic field off. So how can we get measurements of the deflection without turning the magnetic field off? And the approach would be this. Well, what I could do is I could take Earth's magnetic field and I could rotate it. What if I take Earth's magnetic field, let's say it's going into the board right now, but we rotate it so that as the magnetic field rotates, the direction of the force and the direction of the deflection will also vary. What would happen then is if I rotated the Earth's magnetic field all the way around, is that this deflection would be taking place at different locations on the screen, and what it should do is draw a circle. Okay, so let's try that. So I'm going to direct this. Maybe we'll do this as a close-up. Maybe let me go ahead and talk a little bit more about the setup, and then we'll see what this looks like. The idea is this. It's not very practical to rotate the Earth, but what we could do, which would be equivalent, I could rotate the oscilloscope. So by rotating the oscilloscope, what's going to happen here, see that point is mapping out a circle. I'll go ahead and point it in a different direction. Let me turn this up and see if you guys can see this. Let me turn up the intensity. Okay, so I've turned the intensity way up, which we're not going to do during taking the measurements. I want just a fine point. I just want a point that's very focused, sharp, that I can see. Now what I'm going to do with this is I'm going to position this so that it's right at the center of the screen. And then what I'll do is I'll rotate it 90 degrees. Now, if what we've talked about is really going on, then what should happen is, as I rotate the oscilloscope, I'm going to draw a circle on the screen. So let's try that. So I'm rotating the oscilloscope. And by the time I get to here, you can see that the position has shifted. Okay? And then I'm going to keep rotating it. And the position has shifted again. So yeah, what I'm seeing is it's no longer lining up. What's happened on the screen is that we've drawn a little circle. So a little circle has been drawn on the screen. I hope by the time we're all the way around, we're back where we started. Pretty close. Okay. Drifted a bit. Maybe I didn't have it quite positioned and centered. But that's the idea. The idea then is to rotate the oscilloscope. And what that's going to do is that the beam then is going to draw a little circle on the screen. We'll stop at 90 degrees, we'll stop at 180 degrees, we'll stop at 270 degrees. We'll take measurements. So I'm going to get measurements initially, and then at 90, and then by the time I've got the y and the z coordinates, so let's see, the first y and z coordinate is going to be 0.0 and 0.0, because we're starting at the origin. Now this, step back a little bit here, I can't turn off Earth's magnetic field. So when we start off, even though there's a deflection taking place, I don't know in which direction. And so we're going to adjust that so that it ends up centered. So we're actually going to start with the 0, 0, and I'm measuring these in millimeters. And then as we rotate, what I'm going to do is I'm going to take x and y coordinates for each one of these 3 points. Here's one at 90, 180, 270, and then here's the original one. So I'll get some values here, and here, and here, and here. And then what I can do is I can average those. Now, what does averaging tell me? Well, if what we talked about, in terms of drawing these little circles is accurate, then what should happen is that the center of the circle then is going to end up telling us where the beam would have landed if we had turned off the magnetic field. And that's what we were interested in, right? Was if I turn off the magnetic field, where is it going to land? We said I can't turn off the magnetic field, but what I can do is I can rotate it and draw these circles or ellipses. Sometimes they end up being a little elliptical. I can draw these circles or these ellipses around this point, and then I can do averaging to find out where the center of that circle or the center of the ellipse is for that set of measurements. All right? Well, that's basically the idea here. Now, this isn't one of the directions we talked about. So the directions we're going to use here are, this is going to be what x velocity looks like, and I'm going to turn down the intensity here. Don't want to burn out my screen. I do want to focus. Focusing looks good. Okay, so I'll zero it out here, so the coordinates are 0, 0. Now, if I'm looking at x velocity, what I've done is I've taken this formula that we derived with all the vector stuff going on, and I multiplied out the cross product. I just multiplied it all the way out, and then I said, okay, what happens if the velocity is in the x direction? Well, if the velocity is in the x direction, I can't measure magnetic fields in that direction. If the electrons are moving right along a magnetic field line, there won't be any force. I have to have a magnetic field that's perpendicular to the velocity. The forces are going to depend on V cross B. So when we do x velocity, we're going to get deflections in the y and the z direction. And those are going to show up on the screen. So let's see, if this is x and that's y, then this side of the screen is the y direction, and this side of the screen, the top, is the z direction. Now what happens when I rotate? When I rotate this, let me see if I can track down some masking tape. I did. So that I don't get mixed up, what I'm going to do is I'm going to write x on here and place it on that axis. Y, sorry, this is y. And then I'm going to write z on here and place it there, because remember, we have to think of this as not the oscilloscope being rotated, but the Earth is being rotated around the oscilloscope. So I've got to keep the coordinates that I've identified on this screen. So when I write down the y and the z coordinates, they're going to be relative to this and this. So when I rotate this, this is still y down here, and this is z in this location. That's the idea. Okay, so are going to need some masking tape so we can keep track of directions. Now, x velocity looks like this. What does y velocity look like? And y velocity is kind of interesting because y velocity would be towards the front of the room. And again, we can do the 90 degree rotations. But in this case, it's the left side of the screen that is the positive x direction. So when I'm identifying x directions, it's over here to the left of the screen. And when I'm identifying z, well, z is still upwards. So here's x and here is z. Now, how are we going to do the z measurements, right? What do the z measurements look like? Well, it turns out our oscilloscopes, they have feet. So I can actually carefully, very carefully, I can turn this oscilloscope and set it up on its feet. Oh, that's quite a deflection. I've got to recenter that. So that really jumped off the 0 point when I turned it that way. Okay, I've recentered it. Now this would be the z direction. So these would be my z velocity measurements. And again, what I've done is I've taken this cross product, multiplied it out, and identified when the velocity is in the x direction, which components of deflection do I get. And it turns out that when I get a deflection in the y, it's an indication that there's a magnetic field in the z. Everything's perpendicular here. So we weren't kidding when we said this is really a three-dimensional lab. You really have to keep track of all components of the vectors. And then any deflection that I see in the z would indicate a magnetic field in the y. And then that pattern continues for y velocity and for z velocity. Now with z velocity right now, which is what I'm looking at, we have to also ask a question of, well, where do I start? Do I start like this? Do I start rotated here? And so our convention is going to be to turn the oscilloscope so that the right side of the screen, that's my x marker. So I just wrote x on there and placed it here, and that's my y marker. So I've got my x marker here and my y marker here. That really shifted again. Wow. Okay, these are some pretty big shifts that I'm seeing, turning this thing around. And so I'm going to rotate 90. Yep. Rotate 90. Rotate 90. That's a pretty good one to look at. And so, yeah, what I'm seeing is it's drawing a circle on that screen as I rotate that. Okay. So I'm ending up with that deflection taking place. All right, questions on any of this? I know it's a lot of three-dimensional stuff to keep track of. So you can see with this formula, I really just have to calculate that stuff once. Now, this is not how we're going to get the dy's and the dz's. Let's see what we have to do. Okay, so we've got to collect this data. This is what our data tables are going to look like. We have to, let me set this down too. It's probably in the way now. Move this out of the way. What we've got to do is fill in these data tables, find out where the centers of the circles are, and then once we find out where the center, let's say the center of the circle has some coordinates y and coordinates z, what direction is the deflection in? And the deflection, we draw this in red, the deflection is actually back towards the origin. That's where we made that first measurement. So again, the deflection here is, so this is like our 0, 0 point here, right? This is where we started off at 0, 0. This is what we've identified as the center of the circle, and the deflection is directed away from the center of the circle back to the origin. And that means that the deflection components have the opposite sign to y average and z average. When we do these calculations right here, it could be that y average and z average, either one can be positive or negative, right? They could both be positive, they could both be negative, or y could be, y average could be positive and z average is negative, or vice versa. So there's any possible combination of signs. But what happens in this last step is the signs reverse. If y average is positive, well, dy is going to be negative. And if this is negative, dy is positive. So that's one set of signs that you've got to keep track of in your calculations. Once we have the y's, once we have these deflections, once we have these, so it works like this. Let's see. We start with the data tables, we set up the oscilloscope, and we take the measurements in these data tables of the y and z and the z and x and the x and y coordinates. We find average values, we switch them over into deflections. Once we get to deflections, then we come back to these formulas. So that's when we come back. Now, I've written these in terms of how much deflection are we going to get. These then are going to get flipped around. These are going to be used to solve for, well, let's say here's BZ. So if I get deflection Y right here, I can plug that in here, flip the equation around, and solve for BZ. Now, later on, there is going to be a second measurement of BZ. So notice BZ can be measured for x velocities and y velocities. And so that gives me a way of double checking my results. I'm going to get two measurements for each one of the components that we're taking a look at. Okay. So that's it. And then same thing with the BX's. There's two measurements here and BY. Now, a way to check and see if everything's making sense is take a look and see if your BZ's match each other reasonably well. They're not going to be identical. And the two BX's and the two BY's, see if they line up with each other. Now, as far as accepted values, once we've got all the BX's and the BZ's and the BY's set up, we're ready to put them into some kind of a results table, what can we compare with? And so I went online to the National Ocean and Atmospheric something. I went to NOAA and looked up for our location. So I gave Laney College's latitude and longitude and put that in, and it said that currently the magnetic field measured for this area. Now they haven't come in and measured every place entirely. They just go around and do different measurements, and then they find functions that fit that. And then they can interpolate or extrapolate to other locations. So they're suggesting for Laney College, they're expecting that we have a north component of 22.5 microtesla, an east component 5.34, a downwards component of 42.12. Now we talked a little bit about this rotation of x and y. So what we're calling x and y are combinations of north and east. So I went in and did that rotation, and it's in the notes, so you guys can take a look at it in the notes and kind of see how those components got combined. But when I did that, what I was able to come up with is the x direction that we're guessing we'll measure is 22.65 micro, these are Teslas. Why do I have joules? Oh, the first one, that was Tesla. Tesla. There we go. Whew, that was close. So we've got these micro Tesla, any other places, for the magnetic fields, yeah. I did change the number on down because NOAA reported this, the national organization It's not the geophysical something. Anyway, it's oceanographic and atmospheric data. And they gave this as down, but in our coordinate system, that's got a negative sign to it. So I just wanted to point out that in our coordinate system, the BZs you calculate, they better be negative, okay? And the BXs that you calculate, they better be positive. If they're not, stop by office hours, talk to me, and we'll take a look at what you've got and see if we can figure out what's going on. As you can see, there's a number of steps where some of the calculations could get to be a little mixed up, but we can usually track those down. So again, get an early start on the lab, and if you guys have questions, stop by. Now, as far as the Y component, this is much smaller. So it's very easy to get the Y component mixed up. The Y component is quite a bit more difficult to measure than the BZs and the BXs. Those are pretty reliable. So I think that's everything. If I've left anything out, let me know. Ask questions and we'll get everything figured out. But I think that's it. I'm not sure if, I think we've looked at the rotations. I think we've looked at everything. So again, if you guys have questions, stop by and we will get those looked at.